Everyone. In next 10 to 15 minutes, I'll explain ADAS as an end-to-end system from sensing physics to decision and control with an emphasis on radar. The main point is that ADAS performance is not just an algorithmic story, it is strongly shaped by antenna aperture, RF hardware impairments, calibration, and latency. I'll start with the system pipeline, then derive the key FMCW's radar equations, then shift to antenna and RF design rules, and finally connect their hardware reality to detection, tracking, fusion, and safety control. Here is the roadmap for the top. First, I will show the ADAS pipeline and explain why uncertainty and latency dominate safety. Second, I'll review FMCW radar fundamentals and connect beat frequency to range and Doppler. Third, I'll move into antenna and array theory, how aperture drives gain and angular resolution, and what design rules like spacing and taper mean in practice. Fourth, I'll summarize the radar RF front, the chirp synthesizer, power amplifier, antennas, receiver chain, and how noise figure and dynamic range set VL detection limits. Finally, I'll connect the sensing stack to perception and action, range Doppler processing, CFAR detection, tracking and Bayesian fusion, and then decision and control using time to collision and latency-aware stopping constraints. This slide shows the canonical ADAS pipeline. Sensors generate raw measurements, signal processing converts those into physical observables like range, Doppler velocity, and angle for radar, or bounding boxes for cameras. Fusion and tracking combine measurements across sensors and across time, producing stable estimates of objects around the vehicle. Decision logic then chooses actions such as warnings, adaptive cruise control behavior, or emergency braking. Finally, control and actuation convert decisions into steering or braking commands. The key message is that the errors propagate forward. If sensing or processing produces biased, range, or wrong angles, fusion and decision operate on flawed inputs. The key message is that latency is the safety parameter. The system is only useful if the full loop from sensing to braking closes fast enough. So, the architecture must be designed for uncertainty and real-time operation, not just the peak accuracy. Here, we summarize why ADAS is multi-sensor. Radar measures range and relative velocity extremely well, and it works in rain, fog, and low light. Its main limitation is angular resolution, which is fundamentally limited by antenna aperture and array design. Cameras are the opposite. They provide rich, symmetric information, lane markings, signs, pedestrians, but they fail under glare, darkness, or adverse weather. And monocular cameras struggle with metric depth. LiDAR provides accurate 3D geometry, but it is expensive and can degrade in fog or heavy rain. So, no single modality dominates across conditions. Fusion is mandatory because it combines complementary observables. In practice, radar stabilizes metric range and closing speed, while cameras add classification and context. And fusion uses uncertainty to decide how much to trust each sensor in each situation. Now, we move into FMCW radar. We transmit a linear frequency modulated chirp. In complex baseband form, the transmitted signal is an exponential with a phase that is quadratic in time. The slope of the chirp is alpha, equal to bandwidth b over the chirp duration Tc. A target at range r produces a round-trip time delay tau equal to 2 r over c. And if the target has related velocity v, we get a Doppler shift Fd equal to 2v over lambda. The received signal is a delayed and Doppler shifted copy of the transmitted signal, scaled by a complex amplitude beta that includes propagation loss and target reflectivity. The key FMCW trick is de-chirping. We mix the received signal with the conjugation of the transmitted signal. After that multiplication, the output becomes approximately a complex sinusoid at the beat frequency. The beat frequency is proportional to delay and therefore proportional to range. In multi-chirp processing, the slow time phase progression across chirp reveals Doppler. This is why FMCW is attractive. It converts time delay into frequency, which is easy to estimate accurately with FFTs. This slide turns the beat frequency into engineering knobs. Range is proportional to beat frequency. R equals C over 2 alpha times FB, which can also be written as C Tc over 2b times fb. Velocity is proportional to Doppler. V equals lambda over 2 times fd. The two most important design formulas are resolution limits. Range resolution is approximately C over 2b, meaning bandwidth is fundamental lever. More bandwidth gives finer range beams. Doppler or velocity resolution is approximately lambda over 2 times the coherent processing interval. So, velocity resolution improves as you integrate coherently over more time, which usually means more chirps. Now, the trade-off is ambiguity and update rate. If chirps repeat every TR, then Doppler is only unambiguous within plus or minus 1 over 2 TR. That becomes a maximum unambiguous velocity of lambda over 4 TR. So, if you want to measure high speed without aliasing, you need faster chirp repetition. But faster repetition increases data rate and processing load. So, waveform design is a multi-objective optimization. You choose bandwidth, chirp timings, and CPI based on resolution, ambiguity limits, and real-time latency requirements. This slide explains why radar hardware matters. The monostatic radar equation says receive power equals transmitted power times transmit and receive gain times lambda squared times radar cross-section divided by a constant times r to the fourth and divided by losses. The key scaling is r to the fourth. That means doubling the range reduces the received power by a factor of 16. Noise power is kT0 times noise factor times bandwidth. So, SNR scales with transmit power, antenna gain, wavelength, and target cross-section. But it decays brutally with range to the fourth and increases with noise bandwidth. This has two practical consequences. First, antenna gain is not optional. GT and GR appear multiplicatively, and they directly increase SNR. Second, coherent processing is essential. Since FAR targets arrive very weak, we need integration gain from FFT processing and robust detection logic such as CFAR. Finally, RF losses and noise figure determine whether we preserve the theoretical SNR or waste it in the front end. So, radar equation is the bridge between physics, antenna design, and real detection performances. Now, we'll focus on antenna viewpoint. The effective aperture AE and gain G are directly related. AE equals lambda squared over 4 pi times G, which means gain equals 4 pi over lambda squared times effective aperture. For a real physical aperture antenna with area A and efficiency eta, gain is approximately eta times 4 pi A over lambda squared. So, at millimeter wave, because lambda is small, you can achieve significant gain with compact apertures, but efficiency and losses become important. Angular resolution is essentially beamwidth. For a one-dimensional aperture length d, the half-power beamwidth is approximately 0.886 times lambda over d in radians. That means if you want half the beamwidth, you need roughly double the aperture length. So, the key message is range benefits from antenna gain, but angle accuracy and separability depend primarily on aperture. If you want to distinguish closely spaced objects in angle, the most powerful knob is antenna aperture and array design, not a more advanced estimator. And because arrays must be coherent, calibration quality becomes part of angular performance. This slide gives the array design rules you actually use. For a uniform linear array with element spacing d, the steering vector is a complex exponential across elements with phase increment proportional to kd sin theta, where k is 2 pi over lambda. The array vector is a weighted sum of those exponentials. The weights control the trade-off between main lobe, width, and side lobes. The uniform weights produce narrowest main lobe for a given aperture, but side lobes are relatively higher. If you apply a taper like Taylor or Chebyshev, you suppress side lobes, which reduces false detections and multipath sensitivity. But you widen the main lobe and reduce peak gain. The most important constraint is spacing. To avoid grating lobes around broadside, you typically require b less than or equal to lambda over 2. If d is larger, you can get additional lobes that look like real targets at different angles, which is catastrophic for perception. If you need to scan to a wide field of view, the spacing constraint becomes even tighter. So, in automotive radar, designers often choose near half-wavelength spacing and accept a controlled scan range. Then, they manage side lobes with tapering and calibration. This slide explains why real arrays deviate from the claimed theory. Mutual coupling means elements interact electrically and magnetically. So, effective steering vector is not the textbook one. A convenient model is that effective steering vector equals a coupling matrix C times the ideal steering vector. In addition, each RF channel has gain and phase errors due to manufacturing tolerances, temperature drift, and aging. We can model that as a diagonal matrix of complex gains multiplying the ideal received signal. The consequence is that direction of arrival estimation becomes biased. Beamforming peaks shift, side lobe structure changes, and high-resolution methods like music can generate false peaks if assumed manifold is wrong. So, calibration is not optional. In production systems, teams estimate per-channel complex gains using known targets, internal calibration couplers, or factory calibration routines. The objective is to restore coherence across channels and stabilize the array manifold across temperature and time. If you want reliable angle estimates, you must treat calibration as a core part of the antenna and RF design, not just as an afterthought. Now, we summarize the RF hardware. A typical 77 to 81 GHz FMCW radar uses a chip synthesizer, usually a PLL with a VCO, feeding a power amplifier and the transmit antenna. On the receiver side, the antenna feeds a low-noise amplifier, then a mixture that chirps by mixing with a reference signal, then a low-pass filter that selects the bit band, and then an ADC to digitize the signal. Receiver sensitivity is governed by noise figure, and Friis cascade formula shows why the first stage dominate. The noise factor is the first stage noise factor plus later stage contributions divided by preceding gains. That means the LNA and any loss before it largely set the system noise figure. Pre-LNA noise, like feed lines, switches, or filters, is extremely expensive because it directly degrades sensitivity. But sensitivity is only half the story. Automotive scenes have large dynamic range, strong reflectors, and transmit-to-receive leakage that can be huge. That creates a hard linearity constraint. The receiver must remain linear, and ADC must not clip. So you must manage isolation, gain distribution, and headroom so that chain is both sensitive to weak targets and robust to strong interferers. This is where antenna placement, shielding, and RF gain planning becomes inseparable from perception performance. This slide ties the waveform and RF chain into algorithmic pipeline. Radar data naturally forms a cube indexed by fast time within chips, slow time across chips, and antenna element index. The standard processing flow is range FFT over fast time, then Doppler FFT over slow time, producing a range Doppler map. Then, after detection, we estimate angle using antenna array channels. The equation shown is the two-dimensional discrete Fourier transform across fast and slow time. Conceptually, it concentrates energy from a target into a specific range beam and Doppler beam, which improves SNR through coherent integration. Detection is typically done using CFAR. In a simple cell, averaging CFAR, we compare the power in the cell under test to a threshold equal to alpha times an estimate of local noise and clutter power. Alpha is chosen to achieve a desired false alarm probability. The point is that CFAR adapts to varying clutter and noise, which is critical in real driving scenes. After CFAR identifies candidate targets, estimating, angle estimate, and tracking takes over. After detection, we want stable object tracks. A standard approach is a constant velocity state model with position and velocity in two dimensions. The state evolves through a linear transition matrix plus process noise that captures acceleration and model mismatch. A Kalman filter then predicts the state forward and updates it using measurements. The compact form here shows the update. The new estimate equals the predicted estimate plus gain times the innovation, which is the measurement residual. The Kalman gain balances trust between the model and the measurement based on their uncertainties. Fusion is naturally expressed as Bayesian interference. If two sensors produce measurements that are conditionally independent given the state, then posterior equals the product of likelihoods times the prior. Practically, radar contributes metric range and velocity with good robustness, while camera contributes classification and context. Fusion combines them using uncertainty, which improves robustness and reduces false positives. In real ADAS, this tracking and fusion layer is where stability and reliability are largely determined. Now we close the loop. A common safety metric is time to collision. If range is R and the range rate is negative, meaning closing, then TTCs are divided by minus R dot. Low TTC indicates imminent risk. But any decision rule must incorporate latency and vehicle capability. The stopping distance under maximum deceleration is v squared over 2a max. In addition, the system has latency, sensing, compute, and actuation delays. During that latency, the vehicle traverses additional distance equal to v times p latency. A conservative safety condition is that the available range must exceed the latency distance plus stopping distance plus a margin. This connects everything. If the antenna or RF chain reduces detection range or if processing increases latency, the safety margin shrinks. So, ADAS design must jointly optimize sensing quality, calibration, processing load, and control thresholds under real-time constraints. This is why ADAS is fundamentally a core design problem across electromagnetics, RF, estimation, and control. Let's conclude with the key takeaways. FMCW radar converts propagation delay and Doppler into beat frequency, and bandwidth and CPI set the fundamental range and velocity resolutions. Antenna aperture determines gain and bandwidth, and array spacing and weighting determine whether you avoid grating lobes and control side lobes. Real arrays require calibration because coupling and channel drift will directly impact angle estimation. The RF front end limits detection through noise figure and dynamic range, especially under leakage and strong reflectors. Finally, the processing and perception stack CFAR detection, tracking, Bayesian fusion, and decision and control must be designed with latency-aware safety constraints. The closing message is that ADAS is core design, electromagnetics, RF, arrays, inference, and control under latency. Thank you.